Hello everybody, welcome to the lecture on EC368 Robotics. We'll be dealing with two topics in this lecture. The first one is Singularities and then the inverse Jacobian of module 5 of Robotics. Now Singularities, just look at this diagram of the robots. These represent singular configurations. Now for example, look at this one. Here we see that the wrist center is actually intersecting one of the axes of the z-axis of the robot. Okay, so in this case what happens is when the robot rotates around this axis, okay, this is the first axis over here. When the robot rotates around this axis, the wrist center is not going to move anywhere else. This whole thing will just rotate around like this, okay, and the wrist center is going to be there itself. Alright, so this is one example of a singular configuration. Let us see formally what is a singularity. We have already studied about the Jacobian. So we know that the Jacobian is a 6 by n matrix. It is called J. It is a function of the joint variables Q and it defines a mapping. Okay. So the velocities over here of the end effector x dot, it is represented by a vector x dot, is equal to the Jacobian matrix, which in turn is a function of the joint variables into q dot. Q dot is the vector of joint velocities. So the 6 by n Jacobian matrix actually defines a mapping between the vector q dot of joint velocities and the vector x dot is equal to v comma omega transpose of the end effector velocities. So then using the Jacobian matrix, for a given end effector velocity, we can determine what are the joint velocities, or given the joint velocities, we can determine what is the end effector velocity. That is the importance of the Jacobian, and we had seen this before. Now, infinitesimally, this x dot, we can write it as dx is equal to j of q into infinitesimal change in the velocity, that is dq. Okay, so this configurations, we had seen in the previous slide some diagrams, the configurations that decrease the rank of j, are of special significance, and these configurations are called singularities. So positions of the joint variables q, when they are such that j of q has a low rank, then such configurations are called singularities. To understand singularities better, let us look at an example. Again, I would request you to keep your notes with you to make the derivations and the equations a little more clear. Now, consider a two-dimensional system. Again, we had seen the infinitesimal, so dx is equal to j into dq. Let us consider j is of this form. We are actually studying it in a very small way to make you understand what it is. We know that our J matrix is actually a 6 cross n matrix, but we are just showing it with this 2 cross 2 matrix. Okay, so dx is equal to this matrix J into dq. Now, if I'm going to write dx, let us say 2D system. So there's an x component and a y component in dx. So dx is the x component inside d capital X and dy is its y component. So I can write dx from this equation as, and then there are two, let us assume there are two joints here. That is, we have q1 and q2. So in this dq will be actually dq1, dq2. Okay. So dx will be equal to 1 into dq1 plus 1 into dq2. So dq1 plus dq2. What will dy be? Dy will be 0 into dq1 plus 0 into dq2. That will be equal to 0. Now the rank of this Jacobian is 1. Okay, we had said that for singular configurations, the rank of the Jacobian will be very low. So now the rank of the Jacobian is 1. You can see that if the joint variables q1 and q2 change, there will be a change in dx. But if the joint variables q1 and q2 change for this particular configuration of the robot, okay, there is no change in dy. Alright, so any vector dx having a non-zero second component in this case, it actually represents an unattainable direction. So in this direction, you are not able to move, unattainable direction of instantaneous motion. So this Jacobian itself is not a constant. It keeps varying with different configurations of the robot. So suppose as an example, if the Jacobian is like this, we are seeing that we are not able to show an instantaneous motion in the y direction. So this is an example of a singular configuration or an example of a singularity. Now, what is the importance of singularities? Identifying manipulator singularities is very important because of certain things. All right. So we had seen from the previous example that the singularities represent configurations from which certain directions may be unattainable. We had seen, no, whatever be the change in Q1 and Q2, there will be no change in dy because in that particular case, dy was equal to 0 and it did not depend upon the Q1 and Q2. So singularities represent configurations from which certain directions may be unattainable. So at singularities, bounded end effector velocities may correspond to unbounded joint velocities. Now, whole reason why we are doing velocity kinematics is for, let us say, a required or a desired end effector velocity. What should be the joint velocities to achieve this desired end effector velocity we want to calculate? But at singularities, we can see that bounded end effector velocities may correspond to unbounded, going very, very large towards infinity, unbounded joint velocities, which are not physically attainable. Similarly, at singularities, bounded end effector forces and torques. The next slide, in the next lectures, we will be talking about dynamics of robots. So there we will be talking about forces and torques. So to achieve a certain or attain a certain desired end effector force or torque, okay, when we try to find out what should be the forces and the torques and the actuators of the joints, we will find that for bounded or finite end effector forces and torques, we may correspond to unbounded or rapidly increasing forces and torques, which are again physically unattainable. Now, again, singularities may correspond to points on the boundary of the manipulator workspace. Module 1, we had talked about workspaces and we said we had talked about reach and all those things, right? So, the points of maximum reach of the manipulator correspond to the boundary of the manipulator workspace. So, many a time the singularities correspond to points. When you reach the points on the boundaries of the workspace, they can be, but not always, they can be singularities. Okay. So singularities correspond to points in the manipulator workspace that may be unreachable under small perturbations. What perturbations, the meaning is variations of the link parameters such as length and offset. When we studied about various configuration of robots and their analysis in module 4, we saw that parameters such as length and offset were very important when we did the forward and the inverse kinematic analysis. So when you're manufacturing a robot or making a robot, when we have decided that there should be a certain length and a certain offset given to various parts of the arm, if there are small variations, small perturbations in this length and offset also, these may cause points in the manipulator workspace to become unreachable, and this may correspond to singularities. Okay, and near the singularities, another problem occurs. There may not exist a unique solution to the inverse kinematic problem. When we talked about the general properties of the inverse kinematic problem in module 4 itself, we had said that there may be no solution to an inverse kinematic problem, or there may be infinitely many solutions to the inverse kinematic problem, and near singularities, this could be the case that happens. Now, another topic that needs to be dealt with is the inverse Jacobian. So far, we've been talking about the Jacobian. Now, we need to find out for a certain differential motion or velocity needed for the end effector. Okay. Then what should be the differential motion or velocity of the joints? Okay. So for the desired hand is your end effector, desired hand differential motion or velocity, we should calculate the differential motion or velocity of the joints. So this differential motion or velocity of the joints will give us the desired differential motion of the hand. So the inverse Jacobian is used to do this. So you can see earlier in the previous slides we had written dx is equal to j into dq, right? Dx is equal to j into dq. That we are writing in a different way. The D matrix, this is your dx matrix only, is equal to your Jacobian matrix into your dq matrix, that we have written as d theta here. That's the same thing. Okay. So now what we're going to do is your d theta will be equal to what is it going to be equal to? If I want to get d theta, I have to multiply this by J inverse. So multiplying both sides of this equation by the J inverse matrix, J inverse into D matrix is equal to J inverse into J into d theta, which means that d theta is equal to J inverse into D. So that's what we are saying. For a desired hand differential motion, this is your desired hand differential motion, we need to calculate the differential motion at the joints. This is the differential motion at the joints. For that, we require the inverse of the Jacobian matrix that we have dealt with at the beginning of this module. Now, for the entire robot, the same equations hold. So, we get d theta is equal to T6 J inverse T6 D. Okay. So, this is for the entire robot. Now, the importance of the inverse Jacobian we can illustrate with this example. Consider a robot that is laying glue on a plate. Okay. So now to lay glue on a plate, it should follow a particular path on the plate to go on laying the glue on the plate. Okay. But not only should it follow a particular path on the plate, it should also move with a constant velocity. Otherwise, some areas of some points on the plate, there will be a lot of glue. Some points of the plate, there may not be enough glue. So if it does not move with a constant velocity, the glue will not be uniform. So here you can see we had talked about the path in module 4, and now we are talking about velocities in module 5. So both are important, we are seeing in this particular application. So previous slide we had seen a very simple equation, that is d theta is equal to J inverse into D. Okay, but it is not as simple as we think, because this Jacobian matrix J itself keeps changing continuously as the robot moves. Okay, so we have to calculate the numeric values of the Jacobian continuously. All right, so to calculate enough joint velocities per second, for accurate velocities, we have to keep recalculating the joint velocities very fast. So to calculate enough joint velocity per second for accurate velocities, this process of recomputing or calculating the numeric values of J continuously, it must be very efficient and very quick.